Okay, in this lesson, we are going to relate what you already know about absolute value functions and what we practiced with absolute value functions in quarter one to apply to quadratics. So what I want you to get out of this is how similar they are, and then we just want to be able to identify key features like we practiced in section 3.1 and 3.2. So to start with, there's like a little bell ringer at the top. And I want us to go through this just to kind of remember what we know about absolute value functions. So it gives you a function right here and asks you to draw the graph of the function and define the key features. So notice this is absolute value. As soon as we see those absolute value bars, we know that this is going to create a V. And remember, we know that these two pieces transform it as well as this, right? Changing the slope. If it was something at the end, this moved it up or down. It looks like it's subtracting 3, so we're going to go down 3. This one moved it left or right, and this one was always the opposite of what we saw, so this was going to go left 2. And then this changed the slope, right? So we did rise over run of 1/2 when we drew our V. So essentially we could find that vertex just by looking at that equation, right? We knew that it was going to go left 2 and it was going to go down 3. So we can plot that over here on our graph, left 2, down 3. That's the vertex of the function. And then we used our slope of 1/2, and it's a positive 1/2, so we know the V was going to open up. So we go up 1 over 2, up 1 over 2 to create that linear feel there. Up 1 over 2. And we can connect those dots to create the function. Those should be straight lines. Whoops. That's the absolute value function graphed, right? So we can identify that. Now notice we talked about last time, this vertex represents a maximum or a minimum. It's at the bottom of our graph. It's the lowest point on the function. So this one is going to represent a minimum. And then an axis of symmetry, like we talked about last time, is that line that's going to cut it right down through the middle. So if I fold that in half, it goes right there on x equals -2. And we talked about how that's always going to match the x value of the vertex because it has to pass through the vertex. So if we know that vertex, we know the axis of symmetry. And then around the axis of symmetry, there's two sides to these functions. There's an increasing side and a decreasing side. So we're always going left to right. So notice if our little hiker's on here with his little backpack on in his arms, he's headed this direction. He's going downhill first, and then he goes uphill. So what we would say is that anytime we're less than or on the left side of -2, he's decreasing in his height or in the values. When we're on the right side, he's increasing. Oh, sorry, -2. So we can use that axis of symmetry. You can also write that as -infinity to -2 if you like the interval notation, or again on this side that would be -2 to infinity because it's the right side. So there's always a decreasing side and an increasing side, and then it cuts right there at the axis of symmetry. Okay, so over here again it's increasing on the right of our graph. So when x is greater than -2, and it's decreasing on the left side when x is less than -2. And again, if you want to write this as -2 to infinity, and this one is -infinity to -2, that's fine. Sometimes I find we struggle with the infinities and getting those in the right spots, so maybe using the other would be helpful. X-intercepts, remember, are just where they cross the x-axis. So we are going to say it's crossing there at -8, 0. And then it looks like it also crosses at 5, 0. The y-intercept, we look to see where it crosses the y-axis. So it looks like it's crossing there at -2. So 0, -2 is that point. We're going to skip over positive and negative intervals for now, and I'm going to jump to this domain and range. Domain is the -infinity to infinity as we practiced. And then notice our range. Starting at the bottom of our graph, it looks like we're at -3, and then this graph goes up forever. Those values just get bigger and bigger. So our range is the one with the bracket, or some of you like to write y is greater than or equal to -3. That makes sense too, because you just think about it like a wall down here, right? Nothing drops below -3. So essentially that absolute value function, we could draw a quadratic that looks very, very similar. So today, if you'll notice, when we jump down here, our goal is to be able to apply what we know about the absolute value function. So apply our knowledge of absolute value value functions to the vertex form, I'm sorry, you can't read this, of a quadratic. So remember, quadratic means it has a degree of 2. We talked about that last time. So you'll notice this vertex form right here looks so familiar to the vertex form of the absolute value, right? There's a value out front. We know that the a value on the absolute value, if it was a negative a, that meant it flipped it over. So instead of being a v, our quadratics are U-shaped, but that could flip it over, or it could stretch it or shrink it. The h on the inside moved it to the left or the right. That showed us where the vertex went. This moved it up or down. So you can relabel those if you want to remind you. But again, what I want you to realize is that you could identify a lot of these things just from that, right? Our vertex here would just be hk. And we wrote negative hk a lot to remind us that it was the opposite on the inside there. And then remember, the axis of symmetry goes through the vertex, so the axis of symmetry would be x equals that h value, whatever it is, and we could write negative to remember that it's the opposite. But we can find a lot of these key features just from the equation, so that's kind of what our goal is today. And as we move down, you'll kind of see that that's the case. And there's a lot of words on here. I already defined most of this, so we're just going to do some of the examples, but one of the terms that's a little bit new is this term concavity. Concavity just means, is it concave up or concave down? Is it opening up or is it opening down? So just remember, if the value out front is positive, if it's bigger than 0, then your graph is opening up. So it's generally opening up. Oh, that's a terrible U. Should be symmetric. When you have a negative out front of your equation, that's when you're looking at one that's going to open down. And that's important when you're identifying your range. So this range, right, would be different than if the graph is going up to infinity. So we want to make sure, if you ever are just trying to understand the equation, I would just draw it up or down, draw yourself a little diagram. Again, the axis of symmetry just passes through the x value of the vertex. So if I'm looking at this example function right here, y is equal to 2x minus 6 quantity squared plus 1, this value tells me where it went left or right. That's my x piece. So when I'm defining my axis of symmetry, I really just pull that value out. So axis of symmetry here would be x equals 6. Going back to the concavity, if I want to know if this graph is going to open up or down, I look out front to see if it's a positive or negative leading coefficient. 2 is positive, so this one is going to open up. Again, we could find the vertex, right? The vertex is determined by finding that hk value. So if this is the one that we're looking at, y is equal to negative x plus 4 quantity squared minus 3, our vertex comes from the 4 and the negative 3. Again, we do the opposite of the h value, and then we use the k value there. Notice out front, this graph has a negative as its leading coefficient, so this one is going to be concave down. This one's opening down. Max or min, again, this is a term we're going to use a lot. So know that the k value is the max or the min. So really it's just the top, the vertex, or the bottom vertex. If your graph is opening up, so just kind of think about it. I'll draw a little parabola over here. If it's opening up, notice your vertex is the lowest point on the graph. So that's going to have a minimum. If your graph is upside down, so it's reflected, then you have a maximum up there at the top. So that's really just the k value of the vertex, whatever one you're looking at, but it's a high point or a low point. Next on here, it talks about domain. The domain for any quadratic function, right, is going to be all real numbers, unless it's restricted, and we're doing like an application problem. But as we just do all of these functions, we're going to put negative infinity to infinity or all real numbers. So those are the big ones. The vertex, the axis of symmetry, a max or min value, and then the domain stays consistent. When we talk about the range, now range really you just need to think about it, is it opening up or down? So again, if it opens up, the a value is bigger than 0, it's positive, then the range is going to be from that k value up to infinity, right? It goes up forever, so you have that written right there, k to infinity. If it's upside down, now your range is coming from negative infinity and it's coming all the way up, and then it stops at the highest point on the graph. So that's negative infinity to k. So you can kind of see those written that way, or for those of you that like it this way, it's also listed there. So for example, if we were taking this equation right here and we wanted to find the domain and the range, the domain again is negative infinity to infinity, or all real numbers. The range on this one, we look out front. So in the very front, our leading coefficient is negative, right? Which means that this graph is opening down. So we would say it comes from negative infinity and it goes all the way up until the k value. Now notice there's no h value in there, h is 0. But the k value there is a 1, so we could write our range. Or again, if you want to say y is always less than or equal to 1, that's great. And then just kind of reviewing that wording with transformations, it says what transformations have changed f of x from the parent function. So just kind of recognizing this has been shifted up 1. It's stretched by 6, so that thing's going to get steep real fast. And then it's been reflected as well. So we can tell each of those transformations very similar to the absolute value. All right, the last one we're going to look at is the y-intercept. So finding the y-intercept, we've talked about when you solve a function, you find those x-intercepts. Those are the roots or solutions. But a y-intercept occurs when x is 0. So if we let x equal 0, or in other words, substitute 0 in for x to the original equation, we just have to solve for y if we want to know what that y-intercept would be. So for example, if this is our function right here that I just boxed, we would just put 0 in where we see the x and then solve for the y value. So we would have 0 minus 2 squared minus 4 equals y. And then just make sure you follow order of operations. So start inside the parentheses. That would be like 0 minus 2 is negative 2. Negative 2 squared, so negative 2 times negative 2 is a positive 4. 5 times 4 is 20. And then 20 minus 4 gives us that 16. So as a y-intercept, we would say 0, 16. That's where it would cross the y-axis. All right, let's put it all together. We are going to look at this one. It says use the given equation to determine the specified key features of the graph. Write features using correct mathematical notation. So again, the vertex is probably the quickest one that we can find in vertex form. So we look right here for our h and our k, and remember we do the opposite of h. So if that's a positive 3, we're going to pull out negative 3, negative 9. That would be where the vertex lies on the graph. Now from the vertex, we can figure out everything else. The axis of symmetry, remember it passes through the vertex, so it's just that x value of the vertex. The domain is always negative infinity to positive infinity, so we know that one. The range, if you look at our function, we look out front to see if it's opening up or down. This was a positive 2, so I'm going to draw a little U shape to remind me it's going up. So I'm going to start at that k value, and that k value comes from that vertex. So my y value, and it's going up to infinity. Or in other words, y is greater than or equal to negative 9. Okay. And again, to find the y-intercept, we let the function value x equals 0. I said that really weird. But essentially, we're putting 0 in for x. So 0 plus 3 squared minus 9. We get 0 plus 3 is just 3. We square that, so 3 squared is 9. And 2 times 9 is 18, and then we subtract the 9, so we end up with lots of 9s there. It's a 9. So our y-intercept there is at the point 0, 9. Okay. Let's look at another one. So the next one, kind of the same idea. We look at this and we say, okay, where's my vertex going to be? Well, we look right here, and that's going to be a negative 2 for our x value. This one right here is going to be 8. So our vertex is at negative 2, 8. Again, the axis of symmetry goes through the x value of the vertex. So we've got x minus 2, negative 2, 8. Our domain is the same thing, all real numbers. And again, the range, we look at our original function, we look out front. This leading coefficient is negative, so we know that our graph is reflected. It's upside down. So we want to say from negative infinity up to that k value. So we're going to say negative infinity up to the k value, which is 8 in this case. Or again, y is always less than or equal to 8. Okay, the y-intercept, again, you're just going to put a 0 in to your original equation for x. And remember, you can do this for any function. Anytime you want to find the y-intercept, just let x equal 0. So we simplify, that negative just keeps coming. 2 squared is 4. That gives us negative 4 plus 8 is a positive 4. So 0, 4 would be our y-intercept there. Part F is a newer one from the last one. So this says, does this have a max or a min? So remember, we said this is opening down. So this one has a maximum at the top. And the maximum value, if you look at our range, the top number it ever hits, right, is 8. So it's always that highest y value that we'll ever reach. I don't know why there's a graph on this one. We're not asked to graph that one, so I'm going to jump to the next one. This says, write g of x as an equation and identify its key features given these two functions. So you're given f of x, and then you're given g of x related to f of x. So it wants us to create g of x using the f of x. So what we're going to do is we're going to come over here, and instead of writing f of x, I'm going to actually put in f of x. So I'm going to put in this whole equation. So we're going to put in 1/2 x minus 2 squared minus 4. And then g of x is f of x plus 4. So I'm going to put plus 4 on the end to kind of finish that out. Now if I simplify that, notice the front didn't change at all. We've got 1/2 x minus 2 squared. But this 4 negative added to a positive 4 is actually 0. So you can write plus 0 if you want. You don't really need to. But essentially this is the function we're then going to deal with. So notice here, if I'm looking for my vertex there is the 2, went right to, and then the k value is 0 on this one. So we've got 2, 0. The axis of symmetry again goes right through that value, that x value of the vertex. Our domain stays the same. Should probably pause this and see how you do knocking it out on your own. The range, we look out front to see if it's positive or negative. This is a positive 1/2. So we are going to look at it and say, okay, well this one's opening up. So the range is from my k value up to infinity. So we're going to say from 0 to infinity with a bracket, or y is always greater than or equal to 0. And then the y-intercept, we just take that original equation, 1/2. I'm going to put y equals, so I remember that's what I'm solving for, and I'm going to put 0 in for the x value. I'm going to leave off that plus 0 because I don't really need it. So 1/2, I get negative 2 squared. 1/2 times 4 is 2. So 0, 2 is the point where it would cross the y-axis. So if we wanted to sketch this graph down here, we could use either the original equation or all of these pieces. So if I look at some of these pieces, like here's my, oh, I just erased, yikes. This one. This right here is my vertex. That's where I would start. This is cool because we also know it's going to touch this point. So maybe we could use both of those points to even graph this. So I'm just going to come over here at 2, 0. It looks like that's where my vertex is. Again, that y-intercept was 0, 2, so I know it's going to cross here. And if it has to be symmetric, and that's my vertex, then I know it also crosses over here. So notice on this one, I can create a nice little U shape just using those points. Ooh, it's kind of a U shape that I found. And then it says compare it to the parent function. So remember, the parent function would be sitting over here. Crossing at 1, 1. So if we wanted to compare it, we can either use the graph or the equation itself. This one's been shifted to the right too. So it's no longer sitting at the origin. And it looks like that it's been stretched or shrunk, right? And if we look at the original equation, there's a 1/2 out front. So that means that it's been shrunk. It's definitely wider. So we're going to say shrunk vertically, or shrunk by 1/2. That's it. So today really your practice is being comfortable with that vertex form, knowing what pieces come from where, and then trying out some of that notation.